Welcome back, everybody. This is a review section on force and velocity vectors. We're going to be talking soon about momentum, and momentum is when you have a mass going at a certain velocity, and momentum is very powerful. It's why you don't want to be hit by a truck. But in any case, this kind of prepares you for momentum at the same time it reviews some of the things we've talked about with force and velocity. Also, I've noticed in the past that these two are very easy to get confused. So let's look at these two pictures at the top. The first one says, draw sample vectors to represent the force of gravity on the ball in the balls shown above. So these are force vectors. What are the forces on this ball? Now it's left his hand, so there's no force from his hand on the ball. So the only force on this ball is gravity. So that's, remember, what free fall is. Free fall is whenever there's only gravity acting on a ball or some object. And so if I were to draw the forces, gravity is the only force and it's always pulling down. So in this first case, I've got something like this. Okay, so gravity acting down on the ball each time. But this is a different idea of forces, the idea of vectors. What is its velocity? He's throwing a ball at an angle, which means some of the part of the ball is going up. There's an upness to his velocity and an outness to his velocity. And if you remember, he's moving the horizontal part of his velocity doesn't accelerate. But since there's gravity acting down, there is an acceleration downward. So he is throwing up, and so you have an up component and an out component. And if you remember the parallelogram rule, the vector of where the ball is actually going is going to be in this direction. So there is a velocity kind of along this arc. So you can do the same thing here. This is the same as this one is, but this is much shorter because, remember, the speed is being eaten away as it goes higher and higher away from the Earth. So as it's opposed from gravity, it's going to be eaten up at 10 meters per second. Here it's 0 going up, but it's still going the same going out. All of these outs are the same. Okay, these are easy. Do this first. And the downs will be opposite if you get on this side. This is speeding up a little bit, so let's say 10 meters per second, and this is 20, something like that. Okay, so this one is as long as this one, but it's going in opposite directions. This one, almost hitting the ground, would go way down here. And so the resultant would be the parallelogram rule. It's going to go on this, it's going to go along this line, but it's going to go according to a parallelogram that you can, this would go somewhere like this. Okay, so this is the speed. This is its speed vector, and it's going to hit the ground at a very fast speed, I guess. So here's where a lot of people make a mistake. I've got green arrows going here. I've got green arrows going here. So can I just add this arrow to this? And the answer is no. This is a force. This is a velocity. So velocity can be added to velocities. So you can add this to this and get a vector here. So you could say this velocity has a up-down component and an east-west component. But you can't add say a force vector to a velocity vector. They're different. Vector is just showing you some kind of magnitude, some kind of a number, some measured factor, and a direction. But what that vector is representing can be all kinds of things. Like, for instance, we're not talking about the weight of this ball. We're talking about the speed of this ball. We're not even talking about the weight here. Remember, weight is equal to gravity times mass. So there's a vector of weight that's different from just the force of gravity. I suppose these actually would represent weight. I wouldn't know how to express just gravity with an arrow. So weight is a force. So I suppose this is a weight, I should say. So this would be its weight. This is its velocity. You can't add weight and velocity. That's two things that are different. So let's answer a couple questions. Which velocity component in the previous question remains constant and why? Oh, this is easy. This is review, right? These guys are constant. They're all the same. And why? Okay, so let's say the v sub x, which is your horizontal velocity, because, wait for you to answer something, there is no acceleration. There's no acceleration in the outward direction, so it won't accelerate. If there's no acceleration, then these are constant. If there is acceleration, these change because acceleration is always acting down. So as you go up, it's going to shrink. As you go down, it's going to get bigger. Which velocity changes? This would be the y velocity. Why? Because acceleration acts downward. That's why it shrinks as it goes up and grows as it comes back down. It's important to distinguish between force and velocity vectors. That's what I tried to explain here a second ago. Force vectors combine with other force vectors. Velocity vectors combine with other velocity vectors. Do velocity vectors combine with force vectors? No. No, they don't. Okay. Here's what I said that I'm preparing you for momentum. Momentum is when I've got a mass at a certain velocity and it's going to carry some punch that's able then to transfer energy from one system to another. So like this ball is transferring energy and it has an effect later on the pins. So all the forces of the bowling pin, weight down and support up, are given. So this was weight and this is the normal force, okay, are shown on the ball. Now the ball is moving, and I'm sure there's still some people that would scratch their head and say, how can these be balanced and this be moving? But remember, inertia said there's no net force. An object in motion tends to stay in motion. So as long as this bowl is rolling, weight goes down, normal comes up, and it can continue at a constant speed. So as soon as it leaves your hand, it doesn't get faster, only gets slower as friction opposes it. So they're ignoring friction in this case. But even on a very slick wax floor, there would still be a little bit of friction here, so that you would have a little bit of force in this direction away from motion if motion's going this way. Draw vectors on all forces that act on the ball in B. Well, you've got the same ones that are there before. So you have weight and normal force. You also have, a force acting where? Okay. You have a force that the ball is acting on the pin. And what else? Remember, if the ball is acting on the pin, then you also have the same equal and opposite force that the pin is exerting on the ball. Remember the third law. The third law states that for every action there is an equal and opposite reaction. So when I strike this pin and give it a force, give it a bump, it's also going to act on the ball to give it a bump. Okay. Now once it's broken contact, what are the forces again? It goes back to what they were before, weight and normal force. Okay. And I suppose we could add friction here if you wanted friction, but this force is actually exerted by the pin on the ball. It slows it down because as soon as it strikes, the pins all explode and the ball slows down and then falls into the thing. Okay. I hope you're learning.